Our speakers today are Mike Barsick and Steve Herbsley from Southface. And we really appreciate them taking the time to share the information on various compliance paths with air tightness with us today. I'm going to let Mike go ahead, and it's all yours.
So again, my name is Mike Barsick, and I'm a senior technical person here at Southface in Atlanta. And I have been involved with energy code training for over 20 years now, and a lot of other stuff. I come at the world from the mechanical engineering side of things, but I've also built a lot of houses and remodeled a lot of houses, and I love this stuff. It's a lot of fun.
And I'm Steve Herbsley. I've been in this industry about 10 years, and I've had experience with new homes construction testing, and also I've had quite a bit of experience in the existing homes world as well. A lot of the time I've spent in this industry has been at Southface, but I've also worked as a home performance contractor doing energy audits and energy efficiency improvements. But among that, I also have experience teaching energy codes and a lot of things we're talking about today.
In fact, here's a picture of Steve teaching an EVA track on the 2015 IACC, and that was last week or the week before at the ResNet conference. And there's a picture of me biking my daughter to school today. How's that, Steve? All right. So now, and Steve and I have co-trained in the past. We love. We've taught a lot of certification-based training. Steve still teaches. I don't do as much anymore, but you still teach a lot of the BPI stuff. Building Performance Institute certification. I still am a trainer for ResNet for HERS. I've been teaching HERS since the late 90s. So we've been at it for a while. In fact, this is one of our early publicity stills from our early code training in the 70s?
Yeah, I believe that was the first time we trained together.
That's a really good looking sweater you've got there. I'm hoping we get some comments on that, if nothing else. So driving on, we will, I'm not seeing any comments. I'm sure that they're going to just pour in. Driving on, as Pam mentioned, there's AIA credits, and I always want to mention that we will share all these slides, and they'll all be available from DOE. And there's a fair amount of information in here today, so this is kind of an information-heavy content. But we'll try to hit the high points, and please feel free to follow up with us. Here's kind of what we're going to talk about. Basically making sure you understand what is the code asking us to do in terms of air sealing, and the ramifications of that, I guess I would say, in terms of other codes and what is that making us do, and who can do the testing. And we've certainly learned a lot of lessons in the last half dozen years or so as we've kind of implemented this code in Georgia and other states. So we'll share that as we go along. I think this is sort of the learning objectives would tie into it, making sure you understand the connection between air leakage and loads in particular. We added a little section on that. Making sure you understand that we're really talking about 3 different versions of the energy code today, and how are they similar and how are they different. Steve, you kind of we're going to talk more about this thing called the DET verifier program, but can you just give us the high-level view of that?
Yeah, and we'll give you more details later, but it stands for Duct and Envelope Tightness verifier. It's something that we started here in Georgia when we adopted and amended the 2009 IECC. In the air sealing requirements in the 2009, the IECC, it's not required to do testing for the building envelope tightness. It is required to do the duct testing. In Georgia, we amended it to also, in our state, require blower door envelope tightness testing and duct tightness testing. At that time, we created the DET verifier program to ensure that there are trained and qualified individuals to actually perform those tests on for code compliance.
Right. And it's a great way to sort of help, I guess I would say, help introduce the code into places that maybe don't have a huge array of refrigerators or BPI performers. And there was a question about BPI certification, credits for this webinar, and the answer is you will have to self-report, which I don't think will be a big deal. At the end of the day, also realize there's some kind of good and bad in the way we're doing some things in the code, and let's take a little look at that at the end. So we've got a lot of good stuff to talk about today in the next hour and a half. So we're driving on. Again, our organization is based here in Atlanta. We were founded in the late 70s, and a lot of people in the industry know our executive director, Dennis Creech, who is actually going to retire this year after only 38 years. Can you believe that? That's slacker. You know, we work a lot in the Southeast region, but we also work on the national level, and again, have been entrenched in codes for many, many years. We're not going to go around and ask, I think there were 450 people signed up for this webinar, so we're not going to go around and ask everybody what your role is, but I thought it might be worth touching on. We see the target audience of this, I would say, certainly builders, certainly code officials, anybody on the technical side of things, but also I think if you're in the policy side of things and you're trying to sort of say what are the implications if our state is going to one of the more current codes, what are the impacts, how's that going to impact, what do we need to be aware of? So particularly at the end with the DET program, we'll try to share a lot of important lessons. I would think it's great to go to the PNNL website, energycodes.gov, and you can find a lot of great free information amongst them. I love that they update this slide every month, and it shows kind of how things are tracking. And at the moment, you'll see that the majority of the country is on the 2009 or better. And so, you know, about 28, this does not add up to 50, but 28 of the 50-plus jurisdictions here, states mostly, have the 09, and 10 have the 12 or approximate, and then a couple have the 2015 already. And then there's about 15 states that don't have a strong statewide code or no statewide code. But Steve, what does that mean? They have no code at all?
Yeah. It is, yeah, some of those 15 states that are just in the pale that indicates, you know, no statewide code. Most of the major metropolitan areas do have some version of 2009 or equivalent code, but it's just not statewide adopted.
Right. And a lot of times the big cities actually are fairly progressive in where they are. So this is, I hope, pretty relevant. And again, you'll see these icons on the side over here as we go throughout the day, referring to different versions of the code. And there are code references occasionally in there, and since we're talking about different codes, it may be correct for one version, but they may have changed from 402.4 to 402.5 in another version. So, you know, apologies on that. We'll do the best we can here. Kind of a brief history, you know, for some of you folks that have been in it for a while. Back in the late 90s was sort of the first, you know, really the first national code effort, the little yellow books. They were kind of complicated, and I remember them because they more or less forced us to go to double pink windows. We had a big change in the code in 2000 when for the first time ever this concept of solar heat gain coefficient came along, and that really helped spur the windows to switch to low E. And then in the 2004, but really the 06 version was this vast simplification of code, which is, I think, a very good thing, and basically got rid of, you know, this, let's say, too many climate zones, and just tried to streamline the code to improve accessibility, and I certainly support that. In 2009, we hit the first time ever this need for efficient lighting. That's the first time it showed up. The first mention ever of envelope or duct testing shows up, and many states got into the code, the 09 code, because of the ARA funding. And that was a big jump we'll see. 2012 really pushed the bar in terms of prescriptive R values. And 2015 is basically similar to 2012, but it has this new energy rating index. And where, you know, hers is in quotation marks there. So here's another way of looking at it. One of the big changes in terms of code stringency.
Yeah, well, and hopefully that if you can interpret this graph, it might be pretty self-evident. You can see basically the big drops where you drop off a cliff, going from the 06 to the 09. You can see that the code becomes much more stringent. If you look on the left axis there, that is energy index. You can see that lower numbers are more efficient. So you see a big drop going from the 06 to the 09, and likewise a similar drop going from the 09 to the 2012.
Yeah.
But you do notice that the 2015, like Mike mentioned earlier, a lot of the requirements are similar in stringency to the 2012. And we'll talk more, but one of the big differences is the 2015 offers a new compliance pathway, the energy rating index.
Right. So here's kind of a summary, I guess I would say, of the big changes, because again, I think we're going into the assumption that the majority of the states have the 09 code. You may have something better. Here are the big changes as you go to 12 and then on to 15. The R value gets much more strict. Now required to do a motor test. That's a mandate, and also a visual inspection checklist, and also a very strict duct leakage requirement of basically 4%. Some hot water requirements, and here's the key. We're going to touch on this later. The IRC comes into play in the 2012 and later, basically requiring you to have whole house mechanical ventilation if you have a tight envelope, and you will have to have a tight envelope. Also more lighting, but one big thing is in the 2012 as well as the 2009, there's still no trade-off option for envelope versus equipment. And then that's what really that's probably the major change when you get into the 2015, is it offers a different pathway to look at that, and we'll see that graphically here in just a second. The 09 code, you probably, if you've seen it, it's basically one little book, and it's got the residential part and the commercial part. I think residential chapter 4, commercial chapter 5. When they got into the 12 and 15, they split it up like this, with sort of a commercial half and then a residential half, and just a little layout of it. Steve, finally a non-code picture.
Yeah, and just we're going to be talking about, we already have been talking about air sealing the building envelope, and we just want to go over a couple basics to make sure that we all understand what we're talking about. The building thermal envelope, and essentially that is the barrier that separates the conditioned space from the outside or unconditioned space. It's basically comprised of two components, your air barrier and your insulation, or you could say your pressure boundary and your thermal boundary. And an important thing is that those need to be continuous with no breaks or holes or gaps, and any penetrations need to be sealed. And your pressure boundary and your thermal boundary need to be along the same plane or in contact with each other. You can't have your insulation a foot away from your air barrier. They need to comprise of the same boundary. And of course, some materials can function both as an insulation and an air seal at the same time, and that's just fine too. But for things like spray foam, it'll be both. It'll always be in the same plane. But if you're using air permeable insulations like fiberglass or cellulose, they have to be in conjunction with a air barrier. It actually has to be in contact with it.
Right, so this is just a training slide that we use, and it's showing sort of a house, 3 identical looking houses from the outside, and in each case, the builder chose to define the building thermal envelope in a different manner, and they're all legitimate. The R values may or may not be the same requirements, but the big thing is that you need to be able to kind of draw the thermal envelope and never pick up your pen from the paper. And here you can choose, well, do I want to go across the floor and insulate and not condition the foundation or basement, or do I want to include that? And again, it's all acceptable by code. You just have to do the details correctly and meet the code. So I think that's all we need to say on this. Actually, other than testing,
yeah. One important thing to mention is all these options are possible, and in the design and construction of the house, basically you get to decide where your building envelope is by where you perform your air sealing and insulation. It is a good thing to keep in mind. This affects the how you would do the leakage testing of the house for both the blower door and the duct pressurization testing. we'll find out more in a bit how those calculations are performed, but when you do your blower door, your envelope tightness testing, you're going to need to know the volume of the house to do the calculations, and depending on where your building envelope is defined, you're going to have different volumes. Also important is duct systems that are entirely within the building envelope are exempt from the testing requirements. So if you see on the example one there where Mike has drawn the little X, if you had an HVAC and duct system up in the attic there that's outside the building envelope, and down there the one he's got in the crawl space, those need to be tested for leakage. However, if you look on example 3, where the HVAC and the duct systems are completely within the building envelope, those are actually exempt from the duct testing requirement if they're completely inside the building envelope.
Great. All right, so we'll move on, and we're going to just mention again that the 09 code and the 12 code basically have 3 pathways to show compliance on the envelope. You can meet the prescriptive code. You can do simple trade-offs within the thermal envelope using a tool like ResCheck, which is free from energycodes.gov. Or you can do a little more sophisticated simulation approach, but still you are limited. You can only trade within the envelope. And then, of course, mandatory requirements are air sealing. So the big change, let me get back to here, or here's the prescriptive code that shows the R values that many of you are familiar with based on your climate zone, based on 09. And here's a kind of highlight in red, what are the big changes? And you can see there were significant changes in everything that's red. This is going to the 2012 code. And, one of the biggest ones for us is, the windows got a lot better, the ceiling got a lot better, the walls became R20 instead of R13, and so on. So some big implications here in terms of the prescriptive code. And in 2015, Steve, I think you looked it up, these are 100% identical.
Yeah, this table is the same as the 2012, the 2015.
Okay, so the big thing that 2015 brings with it is this 4th path to be able to demonstrate compliance in terms of the shell, the thermal envelope. And it is the energy rated index, and we're going to talk about it a little bit more as we go deeper into it. One of the implications is that it gives you more flexibility. It allows you to take credit for equipment efficiency. It also looks at appliance efficiency, some things that aren't even in the code. So it's kind of an interesting option. The basic way that the energy rating index works, and I'm going to explain this quickly, is you're going to key in the information about your home into some software, and that's called the rated home. It's what you're going to build, what you're proposing to install, and it's going to simulate that home in 1 year's time, and it's going to say, okay, how many million BTUs does it take to heat, cool, provide hot water, and run lights and appliances? And so here's an example where the rated home is simulated, and let's just say it takes 40 million BTUs to heat that thing. It takes 30 million BTUs to cool it. It takes 30 for hot water, and it takes 50 for lights and appliances. Those are just made-up numbers, and those are annual energy to basically keep the thermostat happy. At the same time, or behind the scenes, it's going to take that same home, and it's going to dumb it down or beef it up, depending on the component, to exactly meet code. And the version of the code, I hear an ambulance, the version of the code is 2006. It's okay as long as we always use the same reference. And so in this example, made up numbers, those added up to be 150, I should say. So the reference home, let's say we simulate it, and it takes, it's going to take more for heating, but maybe less for cooling, and the same for hot water, and more for lights and appliances. So if you add all those up, 70 and 20 and 30 and 80, you get 200. So 150 million BTUs for the rated home over 200 for the, if it just met code, that's a 0.75 fraction, and that multiplied by 100 gives you an index of 75. Steve, what does that mean?
Well, basically that's saying that the rated house is 25% more efficient than the reference home. One point corresponds to 1% of increase or decrease in efficiency. And the lower the number, the better. The lower the number, the more efficient the house. So, for example, if those added up to be, say 50, or the index was 50, then that would be about 50% more efficient than the 2006 code.
And likewise, if you have an old existing home, it might have an index of 150, which means it's 50% worse. So the only other comment, Steve, is that there's also an additional multiplier that I didn't have that it has to do with renewable energy. So if you have a renewable energy source, let's say photovoltaic panels on your home, and they generate, let's say, 20% of your home's annual energy use, you multiply your index by, in this case, 0.8. And so that would drop your index from a 75, basically reduce it by 20%, and that drops it to a 60. So that says the home itself is a 75, but with the power generation, it's effectively a 60. And then, Steve, is that at all controversial about using the renewable energy for code compliance?
Yeah. This is one thing that is across the country has been raising a few eyebrows with the ERI being introduced into the 2015 code. Folks are calling attention to the fact that it's the International Energy Conservation Code, whereas things like solar photovoltaics actually involve energy production. So some are wondering whether that's an appropriate way to address solar. Also, it's not necessarily always the same people who own the solar system as the owner of the building. And that's another area of complication with introducing the ERI. So just all be aware that different folks are interpreting this in different ways, and there's still some debate about it. Some jurisdictions are adopting the ERI and putting a cap on how many points you can take for solar. Others are shooting for not having solar in there at all, and other jurisdictions are just adopting it as is.
Yeah, very good. Okay, so in terms of code compliance for the 2015, one thing you'll notice is that the targets are pretty aggressive, but again, you're getting credit for stuff that formerly was not in the code. So you're down typically in the low 50s. And the benefits, again, are you get a lot greater design flexibility, you get credit for more efficient equipment, more efficient appliances. You are not allowed to trade off to be worse than what the 09 code would allow you to do, so there is a backstop. And you still have to meet the mandatory requirements, things like air sealing and duct sealing and testing and so on. Concerns also, you could say it's a conflict of interest in the sense that the person rating the home might be being paid by the builder. There is actually, unfortunately, a bit of a size bias against small houses. It's a little disappointing, but small houses are kind of penalized, which I'm not sure is what we want. In terms of the metric we use, ACH 50, it definitely favors the volume of a big house. And even the ERI itself, we find challenges with multifamily units because they don't have much exterior shell. So it's a little challenging in some cases for smaller homes. And, you could ask the question, should I be allowed to trade, my insulation down because I have an Energy Star dishwasher? And that's an extreme example. But these are all valid questions. At the end of the day, I think it's worth it because I think you've got a professional, such as a home energy rater involved, which really who does typically understand energy efficiency pretty well. And often the code officials just have so much on their plate that energy code is tough for them to allocate much time and resources to. And then, of course, the builders can market. So there's tremendous opportunity for the builders to market the index. And Steve, if you're looking at buying these two homes and they really like both of them, which one are you going to choose?
I would choose the more efficient one.
Yeah.
And to be clear too, we're kind of interchanging the energy rating index ERI with the HERS index, and they are in fact basically the same thing as in the context of using a HERS index for code compliance. We refer to it as the energy rating index, the ERI.
Right.
But it's, for homeowners, it's sort of like having that fuel economy sticker on a car, but having something on your home. You can have this ERI or HERS index, whatever you'd like to call it, and at a glance, the homeowner can, a potential home buyer can have a nice, easy to understand indication of the energy efficiency of that home.
Right. Okay. So now we talked about sort of the big picture of codes. We're going to get into the mandatory requirements and really focus on air sealing. And then just to kind of segue, one of the first mandatory requirements is this need for a code compliant certificate that is usually mounted on the panel box. Some people say, oh, I'm worried about covering up the wiring diagram. Typically just put a plastic sleeve and just insert the document. It's basically a nutritional label, like when you pick up a box of cereal and it tells you the ingredients. So it's got the R values and the U factors of the windows and the equipment efficiencies and so on. It's also a very good place to put the duct and envelope testing results information because the code originally did not say anything about where it should go. So we felt like that was a good place in Georgia, and then I think the 12 and 15 code picked that up. We also, in Georgia, even require a load calculation has to be summarized on it. And at the end of the day, there's an example of what one might look like and filled in. And I wouldn't say we see it all the time. I wouldn't say that we see it filled in correctly all the time, but at least conceptually, I think it's a neat idea. You can also get several versions of this form on our website for free, and some of them are static like this, and some of them are fillable PDFs. So I'm going to try to discard out of here and see if I can find that. Let's see. So if you go to the southbase.org, a lot of good free information. Go under Learning Center. There's a library section here, and you can find something about building energy codes. And there's this cool little house that you can click on. And now this is set up for the 09 code, but it sort of says, hey, here's what you got to do, and little tools like that. But there's field guides. There's videos to use the field guides. There's a training 10-minute overview video of how to do blower door testing. I should turn off my sound and how to do the test, and it's got great little diagrams and let me see if I got stuff I can show. Kind of walks you through what you're trying to accomplish, and I like this part where showing the pressure dynamics. There's depressurization of the house. Nice little video, free, 10 minutes time. There's a similar one for duct leakage testing as well. So good free information to follow up with. And there's also a training page that talks about some of the trainings we do, and particularly the one about the Duct and Envelope Tightness verifier. It has a lot of good information over here, including here is the static form that we were talking about, which I think I have that pulled up. So that's that one. And here it is blank. You can print it and use it. And here's one of just kind of an example with check marks and stuff filled in. And let me see if I get that. There's also a fillable one, which if you put it's got spaces to put in your information, and you can put in I think I can put in 2000 and, yeah, I was trying to pick one that would look more impressive. So 16,000, and then it'll calculate 7.5 ATH50. It's not smart enough to tell you you failed by a long shot, but it does at least do a little bit of the basic math. And also on the checklist, you can come down here and say, crawl space walls, we don't have a crawl space, so we'll pick NA on that one. But for narrow cavities, yes, we did that. And garage separation, we don't have a garage, but we do have can lighting. And so you just fill in the checklist and then print it out. So again, a nice little tool. There's also some other good free information on this page, including, I'm going to mention later, a white paper that we talk about what we've kind of learned from the program. And so I'll just reference that. bring us back to our presentation. There's one of my daughters. Okay, so Steve, why are we talking about air sealing?
Yeah.
Probably important.
Air sealing is actually very important, not only just for the energy use of the home, but also for the healthfulness and the comfort of it. And if you're not familiar, infiltration, exfiltration. Infiltration means uncontrolled, undesirable air changes, air coming into the house. Exfiltration is basically uncontrolled air moving out of the house to the outside.
And you can't have one without the other.
Yeah, they always happen simultaneously. And that is an energy penalty. It will result in higher energy bills. You can imagine if it's a cold winter night and you have that cold winter air coming into what should be the warm exterior of the house through gaps and cracks, you're going to have to run the furnace or heat pump to heat that air. So it results in higher energy bills. Obviously, comfort, drafts coming in make the home uncomfortable. Another thing that's getting a lot more attention these days is the impact on the healthfulness of the home, the indoor air quality. Air sealing is important because a lot of the contaminants, pollutants that can cause poor indoor air quality actually can come in from the outside of the house through these gaps and cracks. We're talking like pollen and carbon monoxide, those types of things. Another thing that's important, though, is when you do air seal the home, you have to be very mindful about what kind of materials you bring into the house, because just like how that sealing can keep pollutants from coming in, if you bring a pollutant in, it can actually ensure that it stays in the home. And we'll talk about that a little bit more later when we address ventilation. Also, moisture coming in, it could be comfort issues, but it also could be durability. If you had humid air coming into a house that is being air conditioned, as that warm, humid air works its way through the gaps and cracks, it might encounter surfaces that are below the dew point and cause the moisture, the water vapor in that air to condense, especially in wall cavities or behind walls, places like that, so you can get liquid water forming for over a period of time, and person might not even know there's a problem until they start seeing mold growth or something like that.
Right. So pretty important, huh? I guess, I also would like to say, we can snag all kinds of very cost-effective energy savings by air sealing. But there is a point where we absolutely have to give something back. We've tightened up a building, and we've got to provide intentional ventilation. And so the codes today have really, aligned pretty well with building science. And recognize that what we want is a tight, well-insulated structure with intentional ventilation. That way we get the best of everything. And so I think it's a key part of that. And here's some great pictures, just some things we're going to be talking about more and more, air leakage in knee walls and chases and attics and tubs set on exterior walls and plumbing penetration. So we'll get more and more of that. In terms of the code, the 2009 code, I think did a really big jump in terms of helping us to better enforce and better understand air leakage. I always got a chuckle out of this, Steve. It says, number 1, thou shalt air seal all joint seams and penetration. And then number 2 through 11 are a bunch of specific places, knee walls, tubs, and so on. Number 12 is, anything I forgot to mention, be sure and go ahead and seal it. So it was a pretty good cover my rear end statement at the end. And a few specific details for some of these things. I guess there's also I'm going to jump over and show this. There's also a air sealing and installation checklist. Here it is for the 2012 code. I'm just going to jump over and pull it up for the, this is the 09 version. And I'll blow that up a little bigger. What we did, Southwest, we took this checklist and we just put a number by each of the items on the checklist. And you can go down the list and read them, and there's some important detail. We're going to review this 15 one in a second. And then we said, that's great. It would be really nice to have a picture of a lot of these. So we've got a lot of graphics that show, and the numbers illustrate what they're kind of demonstrating. I may have to zoom back out a little. And kind of demonstrate places to air seal. And it's not necessarily the only way to do it, but it's talking about, sort of the details we're looking for. And here's a great one that a duct chase for and a duct boot penetration and so on. And we've got these slides coming up in a second. A tub on an exterior wall, and windows and rough openings, and so I think what I'm gonna do is when we're done, I'll burn this PDF for the presentation, but I'll just include these 13 slides as well, or 13 images as well, so you can download the presentation and get all these graphics, and please feel free to use them. I personally think this is a great one because it shows an attic knee wall with an attic air barrier on the attic side, which is we really stiffened that up in Georgia, and it's helped a lot. And also blocking under the attic knee wall. Just diagrams, I think, just help me. I guess I'm a picture person. You too, probably.
And these, like Mike said, we'll make these available to everyone participating, but these are also available on our website in the library section.
And then the multifamily has its own set of issues. Here's a nice little cutaway of a mechanical closet in multifamily and sort of some of the air sealing locations, and here's one that talks about the stairwell that's adjacent to multifamily units and the bands and that diagram we talked about earlier, and even some details about attic insulation. So hopefully that might be helpful to you. And the 2012. There were a couple of changes between the 09 version of this checklist and the 12, and we're going to see also the 15. One of them that went away, interestingly enough, was the requirement to air seal common walls on multifamily. I guess someone said, how does that save energy? But why would we really want you to air seal the common wall in a multifamily application?
Basically to isolate the units and make sure you're not getting air exchanges between them, but also from indoor air quality as well.
Yeah, and frankly, even when you blower door test, if you don't seal between adjacent units, your unit is going to appear to be leakier than it really is, because normally we do what's called an unguarded test. So it's where is it on here? Common walls, number 15 on my 2009 list, and for whatever reason it disappeared in the 12 version. A couple other tweaks and changes, but otherwise not terribly crazy. Fireplaces has caused tremendous confusion, and the way it was written in 09, I thought they were going to fix it in 12. They almost did, but then they put this gasketed door thing in. So try to explain that. Basically, it says new wood-burning fireplace. Originally, it said new wood-burning fireplaces shall have gasketed doors and outdoor combustion air, and that was in the 09 code. And then we got a letter that kind of said, what we really meant was not the kit, because if you retrofit glass doors on a kit, that could avoid the UL listing. So in Georgia, at least, we kind of said this only applies to a true stone or brick, masonry built on-site fireplace. But then the 2015 code kind of came and said they actually helped to clarify it here. So they say new wood-burning fireplaces, they got rid of the gasketed doors. They now say tight-fitting dampers and outdoor combustion air. So the combustion air we think is a really good one. So that's combustion air to the firebox with a damper and of course a flue damper. It says when you're using tight-fitting doors on factory-built fireplaces, basically they have to be UL listed if you're going to add it to a kit, and then if you're going to do it on a masonry one, it has to be. That's not such a tripping point. It kind of makes sense. Your masonry fireplace, it just says in accordance with UL 907. So it's a fun little area to get lost in the weeds. So here's the 2015 checklist, and Steve, I'm going to pull it up in just a second. But the main thing is now there's an extra column. Can you explain that?
Yeah, and in the previous versions, they addressed the air barrier and insulation in a single column, at the same time. In the 2015, it's a little bit clearer because they divided up into two columns: air barrier criteria and the installation criteria. And so previously, those were just all lumped together, but it makes it a little bit straightforward and easier to read with them in the separate columns. Also, a lot of the items are very similar in the 2015 compared to the previous versions. But as you go through these, if you're looking at them, back to back, if you're reading them together at the same time, you notice that the 2015 offers a little bit more clarity in improved wording and more details.
Yeah, I think they keep getting better. I'm going to say it's still not where I necessarily want it, but it certainly is better. A couple key things, air barriers shall be continuous, and external thermal envelope contains a continuous air barrier. Breaks and joints have to be sealed. It says you can't use air permeable insulation as an air sealing in material. That would be things like chinking fiberglass around window rough openings. Just some details, which I think is a representation of an improvement. It's still kind of vague, though, when it says knee walls shall be sealed. I think more description is useful. It does also mention this need to insulate corners and headers and an R3 minimum. And that is an important detail because that really pushes us towards what we sometimes call advanced framing. Everything, and basically, your rigid insulation on the outside has to be in substantial contact and in continuous alignment with the air barrier. So a lot of good detail there. Rim joists, floors. Floor basically says, wherever you end up putting the insulation, the air barrier has to be continuous all the way around it. I think is kind of the summary I read in there.
And
anything you want to add, Steve? Sorry.
I would say in general that the 2015 does a good job of adding details. There is some notable places where it seems to be could use some improvement if they included more details. Like if you look where Mike's scrolling up here, the plumbing and wiring. In the air sealing, they haven't mentioned anything in there, and it does say in the code basically all penetration should be sealed in the general section. But it would have been helpful in the plumbing and wiring here, since a lot of you'll have wiring going through top plates or plumbing going through the top plates of the ceiling of a building. It would be nice if they called that out specifically and mentioned that all penetrations, plumbing wiring penetration should be air sealed.
Yeah. I mean, they do say 50 insulation, which is nice. They have more detail on tubs that are on an insulated. Really, it shouldn't say exterior; it should say insulated wall. And it's all good. It's making a lot of progress. Here's the big new one, Steve, I guess right here, would be concealed spring corners. That was not in the 12 or the 9 version.
Yeah, and basically the 2015 is just saying if you're going to, air seal around concealed fire sprinklers, it needs to be done in a way that's not going to affect the performance of the sprinklers in accordance with how it's recommended by the manufacturer.
And generally, life safety trumps energy code, I think, is a good way to look at it. Great. Anything else on that? So there's our sort of code references. Here's a bunch of pictures that we're just going to talk about, some common air sealing locations, and some of these have the diagrams in them that we quickly went through before. So here's a classic one, the tub penetration, the pipe on the tub is about 2.5 inches or so, and the opening is big enough to pass a 6-pack of beer through there. Is that how that works? So that might be a code requirement in Georgia. I'm not sure.
This is a very common non-conformity to code, I guess you could say. It happens in a lot of houses. It's often overlooked. The giant gaping hole underneath the bathtub that leads into a unconditioned basement or a crawl space. Something to be on the lookout for.
And we had mentioned this earlier, Steve, about the need to be able to insulate headers, window headers to an R3 or better. There's a number of ways to do that, as well as insulating in corners and intersecting corners. There's a lot of techniques to do that, but you can't have a section of the wall that doesn't have insulation anymore, and that's a good insulation detail. Here's another one. I think we mentioned the HVAC chase. It's always better to have the framers cap the chase with a piece of plywood, say, or OSB or something rigid sheet, and then have the HVAC contractor cut the hole for the ducts to run in. Once this gets several ducts running in it, it's really hard to retrofit Swiss cheese and to fill that up. So that can be a challenge. Here's somebody sealing the boot to the ceiling drywall. Same thing in the floor, and then of course here are the diagrams that show the same kind of thing. So there's sort of miscellaneous stuff. You mentioned tubs on an exterior or on an insulated wall. Here's a great, oops, I I'm going to go back on that one. Wait, I wanted this. This is what I wanted. So the picture on the left is kind of the bad, and this is a second floor jacuzzi tub set on a exterior wall that has a little shed roof, probably a porch. And you can see they didn't run the sheathing, which they should have. And here's a great pathway for, you know, exterior air to basically infiltrate into the home and then basically get in between the first and second floor. And this leads to all kinds of crazy, why is there condensation in my kitchen ceiling and there's a second floor bedroom above it? Here's the pathway. So this needs to be sheathed on the outside. It needs to be insulated, and of course, typical insulation is not an air barrier, and then it needs to have an interior air barrier as well, sort of what you see over here. The picture down here, the builder did a great job. This wall on this side is basically an interior wall, so they didn't do anything. This wall out here is an exterior wall, so they insulated it and they put a thin air sealing sheet material called energy brace against it. This is a garage wall. They did the same thing. So attention to detail with tubs, timing is important to get the insulation and air barrier before the tub is set.
Yeah, the order of operations, you know, oftentimes the plumbing rough-in occurs before the insulation, but, you know, the way to do it in this case is actually, it's that diagram in the lower right. You know, they did install the insulation in the stud cavities and then sheathed over it and then set the tub. But you can see the rest of the wall, you know, it's going to be insulated later on when they, you know, do the rest of the exterior walls.
Okay. So here's a couple of pictures too. Again, we mentioned that tub one. I thought this was kind of funny because you can see someone had bothered to air seal these two penetrations, but perhaps missed the forest for the trees, I guess as we might say. Here was the retrofit ceiling, and I'll share. You live in a newer home, right? And yours was built to a green building standard. I live in a 1920 home, and that was the hole that was in my under my tub. And I'm like, what's holding the tub up? But the interesting thing is, my motivation for sealing that was more about getting better air quality in the house because, you know, Steve, my house when we bought it was very leaky and had a lot of air changes, but it wasn't necessarily healthy. And a lot of those air changes were coming from the very moldy crawl space. And I'm allergic to mold. So, you know, again, it was a pretty low-tech solution to fix that problem. Steve, I'm guessing from your background, you've crawled in crawl spaces before?
Yes, and they're typically not the nicest and healthiest environments you can find in most homes.
Have you ever encountered camel crickets before?
I was about to bring that up. We forgot to mention it earlier, but one of the benefits of air sealing is to limit pest intrusion as well. You can imagine these gaps and cracks. They allow critters to come through, and doing air sealing, you know, helps eliminate that. Yeah, and I was working on this in my crawl space. It's not my favorite place to be, like you said. I'm working on my back, sealing this up. And all of a sudden, the camel crickets, one of them started gnawing on my leg. And I'm not kidding, Steve, I freaked out. And it turned out it was my dog, so it was okay. But anyway, my other great air sealing story was we were doing some Habitat Blitzville homes in the late 90s. And we stayed in this kind of Norman Bates motel. And 2 doors down was a traveling reptile show, and that's not an indigenous snake to Tennessee. That's a 5-foot python that had crawled through unsealed plumbing penetrations from his hotel room several doors down to our hotel room. And honestly, I'm not sure what's scarier, this snake or this guy's hairy back. But maybe I should move on. So see if people are paying attention on that one. All right, so. The other diagrams we talked about, you know, we want to air seal at the band on you know, multiple story buildings, and of course window rough opening. Here he's using a backer rod material. They obviously make a foam that's designed to go for windows, low expansion. This is a great picture. I took these from a training I did in Maryland a few years ago. I really like this. They use the sheathing as the exterior air barrier. I'm a big advocate of trying to make the sheathing airtight. There's some tremendous systems out there that
that really use some very good, that do a great job of integrating the weather barrier as well as the air sealing barrier. But here they use the sheathing as the weather barrier and the main air barrier, but they also ran a strip of house wrap and taped it wherever there was a band, which I think that's a beautiful detail. And that's a place where I think house wrap actually does. Generally, we see house wrap, it's just not sealed properly, and people get the details wrong. I thought I'd show some pictures of it being done correctly. This is a nice job where they actually followed the rules instead of cutting an X in the house wrap. And that's, I'll admit, that's how I was taught. You come in here and you cut an X through over the rough opening, and you get these 4 triangles. The bottom goes down, the left and right go in, the top goes in, and then your window with a flange is basically reverse flashed. Doesn't make sense. So what's the right way? The right way is to use kind of an upside down Y. You cut a slit across the top, and then you cut the upside down Y. The bottom triangle goes down, left and right go in. The top, you actually cut a flap. You flip it up, install the window, and then put the flap back down on it. And so there's a picture of it actually done correctly. This is a nice detail. Moving on, we've talked about cantilevers. We're going to come back to that, but just more details on the air sealing. I think we mentioned the attic knee wall, the air barrier on the back of the knee wall, as well as blocking. And what's going on in this picture?
Yeah, this is a fairly common problem with folks who are almost there, but not quite when they're doing their air sealing. And in case you didn't mention, when we say knee wall, we're talking about a vertical wall between an attic space and living space. If you can see in that diagram up there, you see the shiny silver. They sheathe the attic side of the knee wall with a foil-faced foam board. But one of our colleagues, they did not extend that sheathing down between into the joist cavities. And you see him sticking his arm down there. He's actually holding a digital camera, and that picture on the lower left is the picture that he's taking. Basically, the entire band area between the 2 floors there is open directly to the attic. And if you look, you can see there's some cellulose blown insulation there that is piled up in front of that, but is not acting as an air barrier. And that area is completely wide open to the attic.
And at the end of the day, this house probably will never pass the blower door test, right? Because that's a huge leak path.
Yeah, and an interesting story too. I didn't mention this in my background, but when I got started in 2005 in this industry, it was working for South Faces in the Greater Atlanta Home Builders Association, the Earthcraft program, which was a Beyond Code program in 2005. But it's interesting now is what was Beyond Code in 2005 is now very similar to the current requirements of the 2009 and Beyond Energy Code. So in 2005, I was doing very similar inspections and the testing for this Beyond Code program, which is now mandatory.
Good stuff.
Yeah, and basically, this is one of the things that I would be on the lookout for, because builders would be sheathing their knee walls, and they would forget this detail between the joist cavities, almost guaranteed to fail the blower door air tightness test. And that would be one of the first things I would look at as an inspector. I would go up and move the insulation aside, make sure they extended that sheathing. If they didn't, I would basically tell the builders, you might want to reschedule before I get started, because it's highly likely you're going to fail your blower door test.
Yeah, and that's what the visual checklist for the code can help to help catch those things before you actually waste your time doing a test that you know you're going to fail. Here's a similar picture. This is actually from the attic side. This is a weatherization photo, and you can just see that there is no blocking, and this area is going to need to be blocked. What are these things, Steve? These little white knobs?
Shouldn't be seeing that too much in new construction. You see this a lot in existing homes and weatherization, knob and tube wiring.
Oh, should you lick your finger to see if it's active? Or
I would recommend not.
Yeah, okay, so that needs to be removed before we can air seal and insulate and decommission. But here's, again, new construction. Again, leak. Here's a leak path underneath the knee wall, and here's attic insulation just hanging off in space, so that's no good. No sheathing on the attic. No, there's another one. Here they got sheathing on the knee wall like you were talking about, but they did not block. And again, this makes a lot of cold drafts in the winter time. So and almost certainly will fail the blower door test. I'm not saying this is the only material you could use. Some folks don't want to see the the rigid foam like this exposed on the attic side, but this is a great job of sealing. The blocking has been done. They're going to add loose fill insulation. The knee wall itself has been insulated and sheathed, and the insulated sheathing helps the overall R value. Attic access, the code says that's got to be air sealed and insulated. Here's a very important one. When you have a garage adjacent to the house, you've got issues in terms of how the steps. A lot of times there's a basement on that home, and the steps connect up into the house, and a lot of times we find no air sealing. The steps themselves kind of become a poor air barrier, so that's a very important detail. But more importantly, whenever you have, say, on a slab home, you have an attached garage with, say, a second floor above it, this need for blocking up in this location, that's a very poor drawing, but that is a crucial air sealing detail that often gets covered up. It may even get insulated, but it becomes a giant leak valve.
It's very important for indoor air quality and the healthfulness of the home to ensure that attached garages are completely isolated from the living space. And you know, here's a picture. You can see the daylight shining through. Imagine an attached garage on the other side of that. Any penetrations you might have in the ceiling of the garage, from the garage door opener, light fixtures, when you have automobiles running in the garage, or even some of the paints and other materials, gasoline that people might store in the garage, the air can travel up through the penetrations in the garage drywall ceiling and get in the area between floors and then migrate into the house. So it's, you know, very important, not just for energy, but for the indoor air quality.
Love it. Okay, and last kind of big detail is it's a small joint, it's a small leak path, but it's very, very long. So it's this interior wall plate. And here's a truss roof assembly with an interior wall, and they're going to hang the drywall, and the drywall gets mudded and taped from the inside. But if you go in the attic, there's a crack right here. It might be 1/8 of an inch, but the problem is it's hundreds of feet long, and it turns out that can really, after you get all the big holes, that can actually be pretty significant. So there's a number of ways to try to seal that, but just remember, the flat ceiling, your only air barrier is a 1/2-inch piece of drywall, and it can work, but you've got to pay attention to the details.
And and one thing we don't show in this picture, but it is important to mention, we mentioned the wiring and the plumbing penetrations earlier. The top plate in this picture doesn't have those penetrations through them, but typically you would often have wiring and plumbing coming through that top plate, and it's very important to air seal around those penetrations. As Mike is kind of sketching there, if you have an open hole, the attic air can get down into the stud cavity of the interior wall. It might travel into the home through a electrical socket or outlet, but even if the air itself doesn't actually travel into the living space, having that attic air in that wall cavity inside the home, you know, if it's during the hot summer, that interior wall, the surface will be hot, and it'll increase the cooling load on the house and decrease the comfort. Also, if there's any moisture in that air, it could cause durability problems. You know, if it condenses in those interstitial cavities, you know, those behind-the-scenes places.
Yeah, good point. So you have a picture of plate penetrations, yeah. All right, very quickly, I think most people are kind of up to speed on this, but the option of a blower door test in the 2009 says you have to be less than 7 ACH50. That means air changes per hour when the building is kept at 50 pascals. Another way of thinking that is, you know, if I do a test on a house and I hook up a blower door and the volume of the house changes out, if I keep the blower door keeping the house at 50 for 1 hour, how many times would the entire volume of the house change out? And the answer is it has to be less than 7. And so the term CFM50 is unique to every house. Every house, depending on how tight or how leaky it is, will get its own unique answer, CFM50. And we want that number to be the 09 code puts a pretty doable target. Less than 7 is pretty doable. As you get into the 12 and the 15 code, basically most of the country has to be less than 3, and it's kind of weird, it says not exceeding 3 air changes per hour. So I guess it's less than or equal. That's kind of some confusion about that. When you get to basically the Gulf Coast, most of Florida, the climate zone 2, they say less than 5. But everywhere in the country has to be less than 5. Most of the country has to be, in the 2-point-something range. And here's the formula. Notice it takes this blower door number, which is cubic feet per minute, multiplies it by 60 minutes in an hour. So it's really cubic feet per hour divided by the volume of the home in cubic feet. And that's where, unfortunately, big homes get a big sort of easier time because large homes have large volumes. And the home can be pretty leaky and still essentially pass code. So it is a little bit biased, or more than a little bit biased. Okay?
And a quick reminder, too, the 2009, the blower door test wasn't required. It was optional to do the blower door test or the checklist. But starting with the 2012, the blower door and the checklist are both required.
I think we have that coming up. And then the implications of this, if your state is on the 12 IRC or later, basically in section 303, it says, essentially, if you're tighter than 5, you've got to have a whole house mechanical ventilation system. So once you get to the 12th cycle of code, you're there. Now you got to build tight and you got to put in whole house ventilation. And they use a table. The table comes from ASHRAE 62.2, but and this is the 2010 or 7 version. The table, based on this formula, the table tends to round up. And so that's just an important detail. In terms of the IRC, they just use the table. And I thought I'd share with you, we've been involved with a compliance study in Georgia, and we tested about 90 homes that randomly selected around the state. And remember, we have to be less than 7. Our median was, average was around 5, and only a few were actually worse than 7. So in the conclusion, half the homes we tested would be required to have a whole house mechanical ventilation system. I would say we did not see that necessarily. And here's a really quick overview of ventilation. There's a lot more to this, one of our favorite topics, so maybe if you're interested, maybe ask Pam and let us come back and do one on ventilation. But basically, you can suck air out of the house, you can push air into the house, or you can do both at the same time, and that will sort of affect the pressure on the home. And so in many cold climates, the chief ventilation strategy is just a good quality exhaust fan that runs all the time. May not be appropriate for all climates like the humid south. There's energy recovery ventilators and also HRVs, heat recovery ventilators. These are balance systems that essentially say, well, we've got an airstream coming in that's fresh air. We've got an airstream going out that's stale air. The stale air is usually sort of room conditions. The fresh air might be hot, might be cold, might be humid. And so we can essentially precondition the incoming air with the energy of the exhaust air. Those two streams don't mix, but we can capture some energy savings. And then another one that's pretty common is positive pressure or supply ventilation, where we essentially dump outside air into the main return. And when it operates, the air handler pulls mostly return air, some outside air, and it puts a little bit more back into the house than it took out. So that's why we call it positive pressure. All of these are viable, and some are better suited for certain climate zones than others. We wanted to mention duct testing. A lot more strict.
Yeah, and then and duct testing has been required since the 2009, and the 2009 version allowed some more options, and the numbers weren't quite as stringent depending on the type of test you did and when you did it. You're going anywhere from 6 to 12% of duct leakage is what you had to meet in the 2009. Starting in the 2012, they made that stricter for total leakage with the air handler unit installed. That's 4%. The ducts need to be tighter than 4%. And then if they're tested without the air handler, it's a little bit more than 3%. But whether at rough-in or final with the air handler in there, the duct system needs to come in at less than 4%. When we say 4%, it is actually referring to the CFM 25 result that you get from the duct test divided by the square footage of the served by that duct system. Not to be misleading, it's technically not a percent, but that's just kind of a way of referring to it.
Thank you. Good point. And you know, why is this so important? There's some other details. You know, just if you think about it, so you know, duct sealing is very tied to the building envelope leakage. So, and here's a very, very, very fine drawing I'm doing.
Yeah.
Steve, maybe you could kind of.
Yeah, and
whoa, what was that?
as Mike is drawn here,
Like Ohio.
duct tightness is very important. It has a lot of effect on the performance of the house. You know, starting in the 2012, both duct testing and envelope tightness, you know, duct pressurization testing and blower door testing are required. The duct, holes in the duct system are actually also included in the blower door test and then tested separately with the duct pressurization test. This is because your duct system is actually part of your building envelope. And what Mike is, he's doing better than I could, but what he's attempting to draw there is a house with a air handler and a duct system up in the attic to kind of illustrate this point. And you can imagine if you had a hole in that duct system up in the attic and the duct system's not running, essentially it's the same thing as having a hole in the ceiling itself of the house. One example we use when we do trainings on this is, you know, people might be familiar with having hamsters and habit trails. They would have the hamster cage with the little activity tubes that the hamsters could go run up in above the cage and, you know, do various things. And that's like your duct system. When the hamster's up in that tube, he's still inside the cage, even though he's out the main body of it, you know, similar to the duct system.
I'm thinking maybe more of those water slide parts where you go outside the building and then come back in.
Exactly, but, yeah, but you're still inside. Yeah, you're not being exposed to the exterior.
So this is supposed to represent a blower door test being done right here where we're depressurizing, and you can see air is leaking in through various leak paths. But one of those leak paths could be the duct leak itself. So, you know, this is a pathway, and also the seal at, say, the boot right here, let's say that's not sealed well. You know, that's a pathway. So the duct system contributes to the envelope leakage. I think that's what we're trying to get at.
And without going, you know, spending too much time on it, you know, it's when the system's not running, it's just like having a hole in your wall or your ceiling of the home itself. But when the system is running, it becomes even more serious because then you can have either conditioned air being ejected into attics and crawl spaces and costing homeowners money, or it could be drawing in outside air through in leaks on the return side that needs to be conditioned. But also having leaks in your duct system can change the pressures within the house compared to the outside.
When it operates. Yeah.
When it operates. So actually if you have a leak in your duct system on the supply side, you'll be blowing conditioned air out into your attic, but also that would cause the entire home to possibly go underneath a negative pressure that would then draw in air, outside air through gaps around the windows and doors and things like that as well.
So apparently the house is a system. That's what you're telling me.
Exactly.
Well, I was really hoping we wouldn't dwell on this particular drawing. Apparently we did. It will be on sale at the lobby, so we'll just drive on from that. I think the other big thing we wanted to mention is load counts. Load counts will be affected by the leakage of the envelope. And, you know, the code says, essentially, you know, follow the mechanical code for sizing. And when you go look to the mechanical code, it says we're going to do a manual J load calc, and then we're going to select equipment using manual S, which basically means we're going to meet the sensible and the latent requirements of our load, blah, blah, blah. But the way people have traditionally entered envelope leakage in terms of the house is pretty crude. And so, you know, you have this tightness choice right here, and this is based on, I swear this is from the 70s or maybe the 80s, where it was just like, well, you know, the leakage in your house is the sole function of the number of fireplaces that you have, and then you do this tightness, and your choices are tight, semi-tight, average, semi-loose, loose. So kind of subjective here, I think. I think that's the big takeaway. So. Yeah, we're watching it. So at the end of the day, this is pretty crude. I certainly think for a code-based home today, you would be at least semi-tight, if not tight. Here's a better way to do it: is the software allows you to enter a CFM 50, and so if you've tested the home, you can enter that in, and then it will take it and massage it, and it will come up with its own natural air changes in the winter and natural air changes in the summer, and you don't have to do that. All you do is enter the CFM. If you don't have, if the house hasn't been built and you're trying to do a load calc, what you should do is assume the worst case that's allowed by code as ACH 50 and back out a CFM. So if the worst case allowed is a 5, ACH 50, back out whatever CFM you'd be getting on your home, type that in here, and then you're going to get a much more accurate load calc. So that would be our recommendation. Just tying in the whole interesting thing about load, we've made so much progress on energy codes that we've really reduced the impact of heating and cooling in terms of the total load. Here in the 90s, you know, it was almost 60% of the energy in a home was for heating and cooling. This is an average home. Every home has got its own pie chart. But now here we are for the first time ever in the last little bit that we're finally seeing heating and cooling is actually less than 50%. And obviously we've knocked that down, but our increase in energy use comes mainly from more appliances. Fascinating. Water heating sort of hung in there. Last thing we want to talk about is a program that came about because we recognized the need to make sure people testing had some knowledge of how to do the test. We certainly want to look to and recognize the national industries such as ResNet, which is the HERS industry, and Building Performance Institute, which focuses a lot on existing buildings. But we were worried, and we got the feedback from builders that there's just not enough of those necessarily all around the state or all around the region. And so, today, back in the late 2010, we created this course or certification that was basically giving you just what you need to know for code. And that was the point of it. And it did involve knowledge of the code, and it did involve ability to do math, which is important. So this is basically what it covers: how to set it up, how to get the right numbers, how to crunch the right numbers, and a field exam and then a written test as well. And we always made everybody watch the videos before they showed up. And so any of those people, basically HERS raters and BPI folks are grandfathered in. Steve, you want to add anything?
There was a need for this because, starting in 2009, the code started mandating tightness testing, but didn't provide any guidance on who would be a qualified person to do that. So the DET verifier program, was born in Georgia here to address that need of, a minimum standard of qualifications of who would actually perform these tests.
And it's in at least a half a dozen other places now. So if you are interested in this program for your state, we would love to try to transfer it to you. Probably follow up with Steve or me would be the best thing. Also, we did a little study after about the first year and a half of this being a requirement in our code. And I'm not going to go into this. I have some very word-intensive slides here. But this white paper is on our website if you're interested. Talks about some of the lessons learned and kind of compares, the 09 code with the 12 code at the time and where we were, which is kind of in the middle. And again, we tried to answer some questions ahead of time, like how does this duct leakage test apply to an existing home, and does the air leakage test apply on an addition to a home or on a gut rehab or things like that. So we tried to answer some of those questions, and that picture is showing the cat that's about to eat a cactus. So I had to clarify that. That's a lesson learned, I think, is the result. We learned a lot about how to make this work better, and fortunately, everybody has played nice. So if you get trained in Louisiana or Alabama, and then you want to work in Georgia or South Carolina, you have reciprocity. The DET transfers across. And we're trying to make sure everybody is teaching from a pretty consistent sheet of music. So that's why we've shared it with so many folks that are trainers. And then I also did a study of about 4 main companies that were scattered throughout our state, and we are at climate zones 2, 3, and 4, and what they learned. And some did a lot of testing, some did not so much. And some of the things we learned, and I'm not going to go into all this, but we learned a few consistent things. Code-based homes were, in this guy's data, or this company's data, were about 4.4. Beyond code program homes were about a 1 ACH 50 tighter. So some things like that, and I'm not going to go into it. Duct leakage was another interesting one. Here's probably the key takeaways. We definitely felt like 7 was really attainable, and it has been. And I think certainly you can go deeper. Beyond code programs really show a pathway to help you get there, I think. And sometimes the company did additional services that tended to help. Code enforcement matters. The places where the homes failed and the ducts failed were places where they got the CO anyway. And so when you didn't have anybody checking up behind you, you got what you got. And so the test matters, and having somebody check on the test matters. We also found that at the time, at least, spray foam houses generally perform pretty well. I think that's probably the big stuff here. And then finally, the 12 requirements and 15 requirements are much more strict. You got to pay more attention to detail, but it can still be met. You might consider a phase-in of the tightness. You might consider the last thing I want to show you, which is maybe another way of looking at instead of ATH 50. And then again, don't forget ventilation is another issue that we all have to address now if you haven't been doing this. I'm trying to wrap this up here, Steve, so we can get a little
and we're going through quickly here, but this white paper that Mike has written is available for download on the DT training page of our website. We showed you earlier.
Thank you. The last big thing is to maybe consider a different metric than what the code says. We use one we call it the envelope leakage ratio, but it really just means the CFM 50 divided by the shell area of the house. ATH 50 normalizes the blower door by volume, and that's a mistake. The better way of doing it is, the leaks don't occur through the volume of the house. The leaks occur through the shell of the house. So if you normalize by the shell, it's a better way. And the other option is to say, well, maybe we'll have a staggered ATH 50 based on the size of the home, and we'll make a smaller home, have a little less stringent ATH. If you're going to stick with ATH 50, maybe you just have a staggered one. So these are just sort of different ways you might approach that. Bigger homes have to be lower ATH 50. Smaller homes maybe be a little higher. It makes it more fair across the board. And I think the last thing I have is kind of talking about that concept of the shell, and I won't go into this, but it really is a better way, and it really does allow you to compare a 1,000 square foot house with a 6,000 square foot house. And they're both allow leakage proportional to the size of the thermal envelope. And there's just some spreadsheets that look complicated, but just sort of show ATH 50 bogs down when you start getting to bigger houses. So with that said, we finished on time, on budget. And we can see if we have any questions.
I do have a list of questions.
Okay.
But one of the questions was, repeat what DET stands for, and it's Duct and Envelope Tightness Testing.
Duct and Envelope Tightness Verifier.
Yeah, verifier,
It's all good.
Basically, performing blower doors and duct pressurization tests.
And I wanted to mention, too, that BPI in more recent times has come out with the IDL, which stands for Infiltration and Duct Leakage Certification. And it's very similar in some ways to the DET, but I don't think it has some of the math that I would like to see in it. But it's a great certification about how to set it up and do it, and we would certainly say that's pretty good, or that's good enough, and that would count. That's fairly recent. That was not around when we started all this. And for all I know, ResNet may be trying to come up with something similar as well. Okay, what else you got?
We have a question from ASHRAE standard 62.2. The Q of the fan equals Q total minus the Q infiltration. Basically, in the ASHRAE standard, the nature of this question I'm gathering is you get infiltration credit if you just use the ASHRAE standard. The code doesn't go into that level of detail. They just do a simplified version of it.
Right.
And I'm reading the rest of the question here. Basically, making tighter buildings means you get less infiltration credit. And the person is asking, this suggests there's actually a penalty for making buildings tighter.
You advocate that standard 62 should be ignored. And I'd like to answer. This is a great question. So, Steve, you set it up really well. So first of all, what you're commenting on, the Q fan, is basically the credit for infiltration
does not apply to new homes until you get to the 2013 version of ASHRAE 62. So the IRC version that you're looking at right here is using the 2010 or the 2007 equation to create the table, and all they brought over was the table. So in other words, yes, ASHRAE 62 is a great ventilation standard. I may not agree with everything in it, but it is sort of it's a thing we look to. However, the code lifted the table values, but not the equation, and that includes the infiltration credit portion. So that's where we stand right now with that. In terms of code compliance, you have this code to go by. One other big and important difference is starting in the 2010 version of ASHRAE 62, there's not a requirement. Yeah, there is a requirement to verify airflow, but the code does not. So the code uses only the table, not the equation, and the code requires your design to meet this, but there's no requirement that you verify. So there's some very important distinctions between 62 and the IRC.
And a couple of things to add too is it's important to remember ventilation is not an energy efficiency measure. By having mechanical ventilation actually could cause an efficiency penalty. But it's not all about efficiency. You need to have good indoor air quality as well.
Yep, I'm gonna jump down to that one.
And also, yeah, but real quick too, in the 2015 code, they do have efficiency requirements for whole house ventilation fans. So there are benchmarks in the 2015 code of the minimum requirements for how efficient your whole house ventilation fan needs to be. It needs to be an efficient fan.
That's true. So the next question we got had to do with why are you using the reference home from the 2006 code, and why not a more current version of the code? Well, it turns out it kind of doesn't matter which one you stack it up against, as long as everybody uses the same one. In the very early days of PERS, we actually used to use the 93 model energy code as our reference home. But in the year 2006, they changed it to that, and they said, we're probably going to coast here for a while. It's what everybody is used to. It's what everybody has been marketing. And I'm not saying that we shouldn't ever or won't ever update it, but it's something that has been marketing for a while. So I think that it's probably not going to change in the near term. And as long as we all use it as the same benchmark, it really doesn't matter. So if we changed it to the 2012 or 2009 or something, then instead of having to get a 51, you might have to get an 80. So it's just that we're going to stick with this as the reference home. The next question is, can you compare the fuel index? Well, that was just a.
And most car shoppers, and where this is going at is, a lot of people if it's important to them to find a fuel efficient car, they can just look on the label of the cars for sale, and it gives the miles per gallon. And most people, just know that a higher miles per gallon means a more efficient car. Using the ERI or the HERS index, basically you can assign a number to the house indicating its efficiency. In this case, the lower the number, the more efficient the home. So that's that connection there. For the consumers and builders alike, it's just a very convenient, easy to understand index that you can tell immediately, what's the overall efficiency of that home.
Yep. Very good. So we also had a question about attic walls, and so I want to.
And then when you get a chance, jump back to that URL so people that are jumping off can capture that too. I know you want to show the pictures, but we periodically jump back to that URL where they can draw that. Yeah, there you go.
There's the URL,
Perfect.
and
so, then you can go back to your pictures, but I'm just worried that.
Now I'm going back to where I was. Yeah. That was really good. I hope you got that.
Yeah.
Sorry, Pam.
No, it's just a long URL.
Yeah, so I just want to say, the code says something like knee walls shall be sealed. So we have a specific question about knee walls, and this is actually the reason we changed the language in our code in Georgia to be very specific about this, to require the blocking and to require the attic side air barrier. In my opinion, the code should require that as well. Obviously, if that was a air impermeable insulation, that attic side air barrier may not be required. But I think that is absolutely crucial. And to seal that backside, so again, I'll go to that picture. assuming you don't have issues about fire of the foam being exposed in the attic, that picture I think is really showing what we want to accomplish. And it is definitely to your benefit to have the continuous insulation. There are foam boards that are certainly rated to be exposed to the attic side.
And the details of this question too is referring specifically to the contractors are sealing the seams, and the inspector is also requesting that you seal the perimeter. And basically everything should be sealed and airtight is the answer. You know, the juncture of the foam board, the seams in the foam board. One of the things with the blower door testing is for the person who asked this, if they're looking for a way to demonstrate this to the builder you're working with, if you run the blower door and use a smoke stick while standing in the attic, if you're depressurizing the house, and if you move the smoke stick around the perimeter of the foam board, if you see smoke being drawn into that crack, that should do a good job of demonstrating to the builder that it's not actually sealed there. It is connected to the inside of the house.
There's a question that says, are we training general contractors? The answer is we'll train anybody that shows up. Right? I think that's a fair statement. The next question is,
can you take 2 more questions and then we're going to wrap it up and put it back on the website, the URL. So if they do have questions, we also can get any of those questions over to Mike and Steve. They also have contact information out on one of their slides here as well. So 2 more questions, and then we're going to have to shut the webinar down.
No worries. So the one question was about the exterior shell, and I would say that I am a fan of basically on new construction. I think the air barrier, the primary air barrier, needs to be the sheathing. You know, I'm not saying there aren't other ways to do it, but the sheathing itself is, I think, your best shot at a good air barrier. On a retrofit, on existing homes, sometimes you got brick veneer, you can't get to the sheathing, so you do the best you can with the drywall on the inside. There's certainly nothing wrong with having redundant air barriers inside and out. On new construction, if the sheathing is used as the air barrier, and if the seams are sealed and the penetrations are sealed, I think that can make a pretty good assembly. Where it gets interesting is the weather-resistant barrier. And, you know, I don't want to cause controversy here, but, you know, some people kind of believe that the building wrap can serve as an air barrier. And I guess in theory, if it's taped and done right, it can. I certainly think that it can help. But I've also seen a lot of instances in the field where I prefer to rely on the wrap as basically the weather barrier. So there are some products that do it all. There's some sheathing, OSB sheathing that has a coating on it that basically is like a weather barrier, and then some very nice special tape for the seams. It's a very deliberate message that this is going to be sealed, and I think those work well. I think there's a lot of ways to get to it, but I think ultimately my advice is focus on the sheathing, get that airtight, and then, you know, the weather barrier might be a different product or might be the same. And then, Steve, you want to do the last one?
Ventilation or?
Well, no.
Well, yeah, so, well, Mike mentioned this showing the foam board pictures of the knee wall. It is important. Foam products, if you're going to use them for insulation or air sealing, you need to make sure that you follow all fire safety codes as well. It depends on the particular material and the jurisdiction, but oftentimes using a spray foam or a foam board, it would need to be covered with either a thermal barrier or an ignition barrier, depending on where it's installed. So that is an important consideration. And that's constantly in flux because manufacturers of foam air sealing and insulation products you know, are continually trying to get their products rated, whether or not it needs some kind of exterior ignition barrier or thermal barrier, or if that's actually included in the material itself. So if you're working with foam, make sure you have a good understanding, good communication with the code officials in that area to make sure everyone's on the same page and whether or not what you're doing meets fire safety requirements.
And we keep saying, well, we probably should generically say rigid insulation because there's some, I think we should end on this. There's some great products out there that, like Rockwool products that are rigid and can you know, also add continuous insulation. So we love products that do the job, and we're wide open to opportunities. Pam, I think we've probably gone past our time limit, but thanks so much for the opportunity.
Well, thank you, you guys. You did a great job.
Yeah. All right.
Thank you.
Thanks everybody for listening if you're still around. And we'll send on the slide.